All right, let's paint a picture here. If we look at things purely from the perspective of building artificial intelligence, it's pretty clear we need to pause and completely re-examine our technical foundation. We have to ask ourselves, are the methods we're using right now actually helping us get closer to a truly viable solution? Or, in our increasingly complex reality, do we desperately need a more intuitive and effective method? That is exactly the design philosophy we're diving into today. It's a complete return to the physical essence of things, and really, it's a return to the very essence of science itself. We're no longer just piecing together fragmented bits of data hoping to force an answer. We are looking at a massive, fundamental shift in how computing works at its core.
So to really understand this paradigm shift, we're going to use a super simple example, the classic pendulum. Often, when we're taught physics, we start by yielding to simplified problems, right? And that can trick us into thinking reality is just as neat and tidy. By looking at this simple pendulum, we're going to step into what feels like the absolute magic of the viable analog world. But here's the secret. It's actually not magic at all. It's just that the digital age has severely weakened our physical intuition and our foundational thinking abilities over the decades.
Now, before we get too deep into the weeds, we absolutely have to anchor our terminology. Because the difference between simulating a physical event and physically being that event, well, that distinction is the entire core of our journey today. Simulation, which is basically the engine of our entire modern digital world, is just a discretized, numerical approximation of reality. It's an illusion. Analog, on the other hand, that is pure physical existence and continuous, uninterrupted behavior.
Think back to your early physics classes. We learned that pendulum math is incredibly clean, right? The ideal equation is super elegant, focusing only on the length of the string and gravity. But take that out into the real world. Whether that pendulum is swinging in water or a vacuum, or dealing with the heavy bob bouncing on a stretchy string, that movement is insanely complex. It is packed with chaotic variables, friction, and fluid dynamics that our nice, simple equation just completely ignores.
And this right here perfectly illustrates our massive digital blind spot. For decades, to make a computer calculate a swinging pendulum, we've essentially written code to chop time up into tiny discrete steps. We use numerical integration to just constantly guess and approximate reality. But what if we took a totally different route? What if we built an analog circuit that physically becomes the pendulum's exact differential equations? You literally swap out the pendulum bob for a capacitor. You swap gravity for voltage. You swap air resistance for electrical conductance. You flip the switch, and the circuit simply exists as the equation.
The implications of this are wild. Let's say you want to change the environment of your analog circuit. You want to see what happens when the pendulum moves from swinging in the air to swinging in water. You don't have to rewrite a single line of code. You don't run a complex mathematical solver. You literally just adjust a single admittance value on a dial and let the hardware naturally find its new steady state. Which honestly brings up a pretty profound question. When we use standard digital computers, are we actually solving physics, or are we just taking a massive resource-heavy detour to evade it?
The scale of this detour really hits home when you look at professional simulation engineers. Get this, when they run a high-end car crash simulation with something like 280,000 degrees of freedom, calculating a mere 20 millisecond event can easily take 40 hours of computation. 40 hours! And that isn't because we lack computing power. It's a fundamental flaw of using digital, Newtonian iteration to artificially fight against the natural flow of energy in a physical system.
Now let's contrast that 40-hour wait with something called the Fully Analog Computing System, or FACS for short. This system proves that the exact same set of differential equations finds its natural relaxation state on an analog circuit array in just 1 microsecond. You heard that right, 1 single microsecond to physically solve the exact same problem.
These numbers are absolutely mind-blowing. And to be clear, these aren't just theoretical modeling results. These are undeniable physical limits measured in the real world. We're talking about the equivalent of 33.3 teraflops of computing power, an efficiency of 666 teraflops per watt. And because it's a physical, continuous system, it completely bypasses the digital bandwidth bottlenecks we're so used to. Its speed is limited basically only by the speed of light. It definitively proves that when approximate physics goes toe-to-toe with actual physical reality, the analog hardware just completely dominates.
So what does this all mean for the future of artificial intelligence? Because right now, the whole industry operates on the assumption that AI intelligence requires massive data, unbelievable GPU power, discrete clocks, and running millions of discrete mathematical steps. But looking at this foundational shift, we have to ask, is your AI calculating, or is it existing? Just think about it for a second. Our own biological brains do not function like digital computers at all. You don't think in megahertz. Your brain doesn't have a clock speed or discrete sampling rates, and it definitely doesn't process reality in digital epochs.
No, a biological brain relies purely on continuous time constraint relaxation. It is quite literally a physical system naturally finding balance.
What's so fascinating is how perfectly we can map this physical analog hardware directly onto biological neurosystems. It's a one-to-one match. The voltage of a node in the circuit physically represents the continuous membrane potential of a brain neuron, no discrete digital spikes required. The actual physical wiring of the hardware naturally acts as the synaptic weight, and the way the circuit physically relaxes perfectly mirrors mathematical cognitive convergence. It's physical proof that thinking is basically just a physical system finding its steady state.
Let's look at how this plays out in extreme scenarios, specifically with what's called the L5 concept processor. Imagine a system is hit with an unexpected noise level of 0.04. A traditional digital AI will essentially panic. It'll hallucinate, maybe crash, or get stuck in an endless loop of error correction. But the analog hardware? It just auto-decelerates. It smoothly shifts its time constant from 16 picoseconds down to 41.5 picoseconds to ensure a zero-error decision. It's exactly like a living organism instinctively slowing down its thoughts when it's under stress to make sure it makes the safe, correct choice. No brute force algorithms, just physical hardware naturally buying itself time for absolute accuracy.
This creates a massive dividing line between what we call a digital twin and being analog native. A digital twin always requires a GPU to painstakingly drive simulations, step by step, limited by artificial, man-made clock speeds. But in an analog native system, once the power is on, the hardware literally is the simulated object. This goes way beyond just having a competitive edge over digital simulators. This is a fundamental dimensional strike against the traditional von Neumann bottleneck. We are completely rewriting how machines interact with physical reality, limited only by the ultimate thermal noise of the universe.
Now you might be thinking, okay, where are all these physical chips right now? Well, the innovators behind this have already mathematically defined the entirely new computing coordinate system called CSDL version 1.4. This framework establishes the complete math, finalizes the full hardware mapping tables, and completely proves the noise resilience using strict circuit theory, meaning the blueprint is undeniable. We don't even need the physical chip in hand right this second to prove it works, because the math already fundamentally dictates reality.
There is a brilliant quote from the source material that sums this up perfectly. The chip is just printing. We've already delivered the manuscript. Any 40-nanometer process can reproduce it. Physics cannot be plagiarized, only verified. It's a lot like how Einstein mathematically rewrote spacetime decades before we ever had the technology to split the atom. The framework dictates the physical truth. Getting a chip manufactured is just the inevitable byproduct of discovering the math. Ultimately, this forces us to confront a really uncomfortable question about modern machine learning. When our digital models are just chugging through massive data sets, are they truly learning anything, or are they just overfitting and memorizing data? An analog circuit, on the other hand, genuinely becomes the decision itself through pure, unadulterated electronic relaxation. At the end of the day, as the explainer points out, the answer really just boils down to basic Ohm's law.
I'll leave you with this provocative thought to chew on as we wrap up today's explainer. If the true essence of thought isn't symbolic digital computation, but is actually physical relaxation finding a steady state, do we really still need a Turing test to measure AI, or do we just need an oscilloscope? As we step into this mind-bending, analog-native future, maybe the ultimate measure of true artificial intelligence won't be a chat window conversation, but simply observing the continuous wave of a physical reality. Thanks so much for joining me today, and I really hope this deep dive shifts your perspective on the future of computing.